Hello everyone, I'm Yuji Moroto from the University of Tokyo. I'll talk about constant time median filter using 2D wavelet matrix. The presentation will be in the following order. First, I'll introduce the median filter and the existing implementation methods. Next, I'll introduce the wavelet matrix, which is the key idea of this presentation. Then I'll show how to extend the wavelet matrix to be applicative to 2D images. This is our contribution. Finally, I summarize our experimental evaluation and conclusions. A median filter is a filter that takes the median of regions. It is classical denoising filter, and this is often applied as a skin beautification filter. Also, creators often use median filters for melting effects as a simple and available method in any software. In this case, we will filter with a very large kernel size, which is typically conventionally very expensive. A lot of research focuses on accelerating the median filter computation. There have been two main approaches to computing median filters. One approach uses histograms and the other uses sorting-based method. In histogram-based methods, we prepare histograms with 256 counters for an 8-bit image. These methods are fast when the kernel size is large, but slow when the bit depth is large, such as for 16-bit images. The current OpenShift median filter uses this implementation. Another existing approach is the sorting-based method. This method creates sorting networks and finds the median in parallel. It is fast even for HDR images, but becomes slower as the kernel size increases. Thus, the previous methods have been used according to kernel radius and whether HDR is used or not. However, there was no method that was fast enough for large kernel size and also support HDR. In contrast, we propose a completely new constant time median filter method that also works for HDR. This would lead to the use of the sorting method for small kernel radii and the wavelet matrix method for medium to large kernel radius. Next, I'll explain the wavelet matrix, which was the basis of the idea of our method. A wavelet matrix is a data structure that can efficiently answer various interval queries for a one-dimensional sequence of numbers. This has nothing to do with the wavelet transform used in image processing. Wavelet matrix can quickly answer queries such as the kth smallest number in a given interval or the number of values in a given value range. We first compute the preconstruction of order nb time, and then we can compute interval queries. These queries can be computed in order b steps per query, regardless of the length of the sequence n or the length of the specified interval. In addition, only the size of the data itself and a small amount of supplemental memory is required. Because of these features, wavelet matrix has been mainly used in the field of string search, database search, DNA analysis, and competitive programming. In this research, we extend the existing wavelet matrix for 1D arrays to 2D arrays and propose a median filter with an order b log w time per pixel. This supports filtering in constant time for HDR image as well. Since each pixel is completely independent, this method can be parallelized on a per pixel on a GPU, or the kernel size can be changed on a per pixel basis. Next, we will explain how to construct wavelet matrix. We will use an example for a 3-bit value with value from 0 to 7. First, look at the top bit and group it into two categories. In this example, the top bit of 0 is colored blue and the top bit of 1 is colored orange. Sort these into blue and orange groups, keeping the order. Next, look at the middle bit, group it into blue and orange, and sort it in the same way. Finally, the bottom bit, which is even or odd, is grouped into blue and orange and sorted. The operation is similar to the radix sort, but sort from the top bit, not the bottom. The wavelet matrix stores this binary array of blue or orange, that is 0 and 1. It then answers the query. First, let us introduce the quantile query. This is a query that takes an interval L and R and a number k and finds the k smallest number in the interval. For example, in the case of quantile in this interval, 3, we want to find the third number from these 5 elements. I'll now explain how to get this in wavelet matrix. First, count the number of blue boxes in this interval. There are 2 blue boxes in this interval. Since it is the third number we want to find, we know that the answer is the number of oranges in the later half. Since the number of blues in the front half is 2, we know that the answer is the first number of oranges. Next, we will focus on the next later half interval. The number of blues in this interval is 1. Since we want to know the first of these numbers, we know that the answer is in first half. Finally, the number of blues in this interval is 0. Since we want to know the first number in this interval, we know that the answer is later half. Since this is the last step, we can reduce the answer to 1 and see that the answer is 5. Next, I will introduce the range frequency query. A range frequency query is a query to find the number of values between x and y in the interval L and R. For example, this interval 3, 5 is the number of values between 3 and 4 in this interval, so the answer is 2. The range frequency query can be decomposed into low frequency queries. The low frequency query is the number of items that are less than x in the interval L and R. For example, low freq 285 is 3 and 283 is 1. Range frequency can be answered by calculating the difference. Next is how to compute the low frequency query. Let's take the example of low frequency 5. The key idea here is separate counts of less than 5 into count of 0 to 3 and counts of 4. First, the number 5 is 101 in binary. If the top bit is 1, we add number of blue boxes. The top bit of 5 is 1, so we add the number of blue boxes in this interval, add 2 to the answer. The way to find the next interval to look at is the same as in quantile. The next bit is 0, so we don't add anything to the answer. We move on to the next interval. The last bit is 1, so we add the number of blue boxes in this interval. If we look at the answer here, it contains the sum of the number of boxes from 0 to 3 and 4. In other words, the number of boxes is less than 5, so the answer 3 is found. Next is how to count zeros, which was an important operation to answer these queries. First, the simple idea is prepare a sum tables at pre-construction for fast counting. For example, if we want to count the blue zeros in this interval, the difference between these 7 and 4, so 3 will be the answer. This is very fast but requires a large memory space because it requires an integer array of length n to store this table. So we divide this bit array into several chunks. The value of the sum table is recorded for each chunk. When counting, count the number of bits in the chunk and answer the sum with this chunk sum. The bit counting can be computed quickly with the pop count instruction in recent architectures. This allows answering count queries at high speed while greatly reducing memory usage. Now let's talk about our method. Our goal is to compute an interval query for such a two-dimensional integer array. In other words, we need a 2D quantile function that will allow us to specify a two-dimensional rectangular interval and find the kth value within this rectangle. First, flatten this two-dimensional array with x index to one dimension. Calculating 1D quantile with this flattened 1D array is not correct because it increases values that are not needed. For the one-dimensional case, the key operation was to count the number of blue boxes in the interval. In 2D, we want to find blue boxes only for those with x index of 0 to 1 and ignore with 2. To compute this, we consider a new sequence of numbers. This is an array constructing the x index for blue and 3 for orange, which is with all input array. For this sequence, count only the number of values between 0 and 1 in the interval, and we will get the answer we want. This can be obtained with length frequency query in a 1D wavelet matrix. In other words, by having a 1D wavelet matrix inside, a 2D wavelet matrix can be computed. Next is an explanation of the construction. The rules for sorting a number sequence into blue and orange are exactly the same as for the one dimension. At this time, the x index is attached along with the value of the elements. After sorting, process the x indexes. Leave the x indexes in the blue box as it is, and change the x index in the orange box to W, which is the width of the image. When construct a 1D wavelet matrix from this sequence of numbers and keep it. The 2D wavelet matrix use this sequence of numbers to answer queries. Next, let's see how to find 2D quantile. 2D quantile finds the kth number in a given interval. By using this, we can compute the median filter. Now let's take a look at the calculation in practice. First, we will focus on this interval. At this point, there are two numbers between 0 and 1, so we know that the answer is in the later half range. We will calculate the next interval. Since there are two numbers between 0 and 1 in the next section, we know that the answer is the first half blue. We will calculate the next interval. The first one in the last interval is the answer we want to find. Since there is only one number between 0 and 1 in this section, the answer is in the first half blue, so the answer is 4. Next is the evaluation. We implemented the filter using CUDA. This is the computation time when the image size is fixed and the kernel radius changed. Our method doesn't change the computation time when the kernel radius is increased. The sorting-based method is fast when the kernel radius is small, but our method is fastest when the radius of 12 or more. OpenCV is a histogram-based method, and our method is 13 times faster than it. The next results are for 16-bit color. Histogram-based methods were unsuitable due to memory requirements, so OpenCV didn't support them. Our method successfully filters at a constant speed even on HDR image and is over 116 times faster when the radius is 50. Next is the memory usage. In Full HD, 50 MB was required for the wavelet matrix data structure itself and 80 MB for the buffer used to build the wavelet matrix, resulting in a memory requirement of about 130 MB. This is a relatively small amount of memory. HDR in Full HD also required about 300 MB overall. At 4K, the memory required increases in proportion to the number of pixels. HDR for 4K is somewhat larger, but 1.5 GB overall. We consider this amount to be acceptable in an environment where high resolution and high precision image editing is used, but it is little large, which is something we would like to improve. Next is future work. As shown in the previous slide, memory usage is a bit high when dealing with high-resolution, high-bit images. We are currently working on this issue and testing a minor update that will cut the memory usage by about half. We will post any new results on the project page when it is achieved. Second, we have now extended the wavelet matrix to 2 dimensions and have shown that it can be used for image processing such as median filtering. However, we believe that this wavelet matrix can be applied to other image processing, including computer vision. We expect it to have application beyond median filters. Also, we only tried the GPU implementation because we had no knowledge of how to implement it fast for CPUs. We look forward to people pursuing faster implementation of this young data structure as well. Here is a summary. We have extended the wavelet matrix from 1D array to 2D array. In this way, we have present completely new median filter method whose computation time is not affected by the kernel size. Furthermore, it supports filtering on HDR images, which is difficult to do with histogram-based and other methods. Also, our algorithm is parallelizable and can be efficiently executed on GPUs. As a result, our method is the fastest when the radius is greater than 12. Thank you for listening.